Hi there, welcome back, and let's continue our discussion of composite indexes. Okay, so we were in the midst of a discussion about composite B plus trees in which a concatenation of column values makes for the index keys. All right. Well, of course, such indexes are being built to support predicates that mention more than one column. So these are also called multi-dimensional predicates because they refer to multiple dimensions, multiple criteria, multiple columns in a table to decide their Boolean value. So I brought one such query with me, or a template for such a query. And you can see we are operating over some table T here, okay, but there is two columns of T, namely the C1 column and the C2 column. They both are mentioned in a predicate here, in this conjunctive predicate. So I'm not looking deeper into this P1 and P2 at this particular point. We will do so when we consider an example, but for now let's make this more abstract here. Okay, so there is indeed two dimensions. Two dimensions are being involved in deciding this particular predicate. Okay, so let's build a multi-dimensional or composite or concatenated index over the columns C1 and C2 so that this predicate can be efficiently supported. Maybe this is a very important query in our workload and it deserves index support. So, but looking at this particular Boolean expression here, it does not suggest a particular order of the C1 and C2, only that this is predicate P1 and this is predicate P2. Doesn't make a difference for the evaluation of this Boolean expression. I could easily swap the order of the P2 and the P1 predicates here, and this would be still the same predicate. So this predicate itself, it does not suggest any order of the C1 and C2 columns. Shall we build this or this concatenated index to support this particular predicate? Well, I don't know yet. And we know it really makes a difference. We have talked about the order of rows in concatenated indexes that have such composite keys. We've talked about the order of rows, and they might be considerably different. So it really makes an interesting choice here. So let's, for a change, let's observe PostgreSQL and ask ourselves, what would PostgreSQL do? Faced with such a particular situation, will PostgreSQL favor this or this particular index? And maybe this provides an insight and an answer to this particular question. Which of the two indexes is best in this particular case? Okay. So let's switch over to the terminal again. And of course, we will consider our indexed playground table. And you know from the last video, it already had this CA composite index defined on it. I will now add, or I've already added actually, so that we don't suffer from the waiting time here. I've already added the AC index in which the column order is indeed swapped. Okay, so let's look at the state of the current indexed table here. Indeed, we find both indexes. The composite index with A first and with C first, we both are being defined on this index table. So when we evaluate queries now on the index table, the system, PostgreSQL, has the choice of employing the one index or the other. Okay. Okay, so to explore that, let's perform a little experiment here. And I brought such a query. I brought such a query in which the predicate, let's look at the predicate only here, in which the composite predicate is indeed referring to both columns A and C. Both have index support in the two composite indexes. You see that I'm using this range query here, this between and construct of SQL, to define the selectivity, the pickiness of these two predicates. All right, so these two ranges here, these two minimum maximum ranges on the C domain, they define the selectivity of the C base predicate. And these two ranges, one of them is configurable with parameter m, define the pickiness or the selectivity on the A base part of the predicate. So by setting M, I can vary the selectivity of this conjunct here, of the predicate part that refers to the A column. Okay, so for now, as a starter, let's set the M value to 10,000. Okay, and so when I evaluate this query, this will be just like the literal 10,000 here. Looking at the column values and knowing something about the distribution, I've done that before. I know now that the P1 predicate, this first predicate in this line, will be more picky and more selective. All right, it will be more selective than the second part. So let's see how PostgreSQL evaluates this particular query, or how it plans to evaluate it. I'm only doing an explain here. Okay, so the system decides to use the CA index, the index in which column C comes first and in which column C determines the row order. Okay, so yeah, indeed, C has been, on C we have defined the conjunct that is indeed more picky and more selective. And as it will turn out, this pickiness, this selectiveness, the selectivity is the guiding rail that PostgreSQL uses to decide which index to employ here. So let's change the situation. Let's make the second conjunct more selective by reducing the value of M. Okay, so the range will be smaller, less A values will qualify, and well, this becomes more picky and maybe more selective than the predicate above. Okay, so let's see. Let's switch to 7,500 here. Define that and rerun the query. Oh, indeed. All right. Index scan again. Now a true index scan indeed. Probably because of the row order in the heap file of the index table, which is probably clustered according to the A column. All right, but this is of second importance here. Important is that we are now switching to the other index, to the AC index. We have been using CA before. Now we're using AC. Probably based on the observation that the A predicate, the A conjunct now is the more selective predicate. Okay, let's reduce the M even further and make this A conjunct even more picky and even more selective. I think we should see that now the system is, of course, still again using the AC index. The index is primarily based on the A column. And of course, it will remain so if I further reduce this M value and make the second conjunct more selective and more selective. Okay, right. So what we could try now is to find the break-even point. Where's the point, where's the definition of parameter M, where the system really switches over from CA to the AC index. We could perform a sort of binary search here. So let's pick a middle value between 10,000 and 7,500, which would be 8,750. This is the first step in the binary search. Okay, and okay, for that value of M for 8,750, we are back to using the CA index. So the system regards this part of the predicate on the C column to be the more selective and the more discriminative part. Okay, okay, we could further reduce that M value to say 8,000. So the next step, the next pivot value in our binary search. Let's not forget to define that. Okay, and run again. Still the CA index. Okay, so let's make this second conjunct more selective again, and the next value in binary search would be this one. Query again. All right, so now we are back to the AC value. Okay, so somewhere between this 7,812 and the 8,125 bits, somewhere between there, the system probably decides to flip over from one index usage to the other index usage. The selectivity really plays the primary role here. Maybe you find the time, or you find it interesting to find this particular M value for your setup. let me warn you that really the exact value of m that you will find where the switch occurs from one index to the other might vary from system to system, from student system to student system, even from analyze run in and between two analyze runs on your same installation of PostgreSQL. All right. So, but you will find probably very similar m values. They might not be the exact same values. So let this be just said here. Okay. So how come? How is the selectivity the guiding principle here? How does selectivity determine everything? And maybe these diagrams that I've shown you before are of help to explain the situation here. Okay, so what we've built in our experiment has been two indexes, a C1, C2 index and a C2, C1 index. All right, and of course, we have seen this value distribution inside composite indexes before. So if the C1 index, if the C1 column, I'm sorry, is the primary, the major column, then this would be the picture that we see. All the C1 values that agree are local inside the sequence set, and well, inside the C1 group, we will find ascending C2 values. Well, we have seen that before. Okay, so now if we recall what index scan actually means, index scanning actually means to descend the B plus tree from the root toward the leaf level where we find the sequence set, and then determine the subset of the sequence set that will contain the matches for a particular predicate. Okay, so I've indicated such a scan range already here in this sketch here. This would be the scan range, or let this indicate the scan range for the one conjunct on the C1 column. All right. So for a particular choice of parameters, this would be the width of the scan range in the C1 column. Okay. For the same set of parameters, the scan range in the C2 column might be narrower. Who knows? Okay. So this would just be the scan range, and well, in the sketch it's supposed to be smaller or not so wide as the scan range here on the left. Okay, the width of the scan range actually defines the work, the amount of work we have to do while we perform an index scan. The longer the scan range, the more index sequence set pages we have to visit, and the more pointer dereferences, RIT dereferences into the heap file we have to pursue. Okay, so I would rather opt for the version of the index scan that walks the smaller, the narrower index scan range, and that would be this in this particular case. Okay, so smaller index scan range if compared to this index scan range, this would be the index of choice for this particular choice of parameters or index scan width. So we aim to minimize the work that we do. So the more selective the predicate, the smaller the window scan range, the more attractive is the use of that particular index. Okay, so the more selective predicate determines the choice of index. In this particular case, if I had the conundrum to decide for the creation of only one of these two indexes, say my heap file or file system space budget is really tight, I can only afford to create one of these two indexes. I can only afford the maintenance of one of these indexes, the vacuum and the analysis of these indexes. All of this takes time, so I can only afford one of these indexes. I think I would prefer this particular index organized by the C2 column. And why is that? Because it offers the smaller scan ranges for these C2 values. You see that, well, there's a greater number of distinct C2 values than in this particular example, then there are distinct C1 values. So I can expect the I can expect the scan ranges in this index to be smaller in general. All right, so if I had to choose between the two indexes, then this probably would be my choice. All right, of course, it's best to have both indexes around, at least from the viewpoint of query evaluation. Query index maintenance is a different story here. Okay. So there's the rule of thumb. If you have to create indexes, composite indexes for the support of predicates, and you are left with a task to decide the order of columns here in that such a composite index, then that could be a good rule of thumb. If you find that parts of your predicate, maybe this part or this part of these composite predicates, these multidimensional predicates, if you find that parts of this predicate query by equality, and such equality comparisons of course lead to the narrowest scan window ranges. Okay, so equality really asks for just one such group, or maybe this particular group. Let's indicate this group. These are the smallest index scan ranges that I can hope for in these indexes. So if you find that parts of your predicate really use equality, so the equal sign, then this is a good candidate for the column and the predicate that should go first in such a composite index. It will lead to the narrower scan ranges. Narrower scan ranges than range predicates that are based on these larger or less than comparison operators. But this is just a rule of thumb if you are questioning, or if you're tasked with the physical design, the index design of a database. This might be something to look out for. Okay. So much for composite indexes. Well, now there is more about composite indexes in that particular course, but this is about index design for such multidimensional predicates. All right, so selectivity makes all the difference. These are the most selective predicates, equality predicates. Let them guide your physical index design. Okay, so much for this video. There is more to be said about composite indexes in the upcoming video. Maybe you will be around for that. See you then.